Hello all! Today we are concluding our series of webinars on data masking. Today's webinar also explains security in depth, as we do data masking as a security measure to protect data from insiders' threats. In our prior webinars, we have covered different aspects of the data development lifecycle and SSIS. They are listed here on the slide. Prior webinars included SSIS, a first experience, lifecycle, testing with SSIS, ETL versus ELT, and data masking algorithms, among them substitution, shuffling, random, date aging, aka number and date variance, encryption, specifically tokenization, nulling out or deletion, value changes in increments or decrements, as well as custom algorithms. We have looked at the scenarios involving data masking in different environments as they pertain to different insiders' threats based on roles. We implemented a simple life cycle. We did some test cases in SSIS, including regression testing, and showed advantages and disadvantages of ETL, extract, transform, load, versus ELT, extract, load, transform. We gave a definition of data masking. Obfuscating sensitive data elements with false values within a data store while preserving data look, feel, and usability in applications. We listed all the algorithms and showed examples of their implementations. Some algorithms are very simple and fast to implement, while others are very complex and allow for a lot of protection. We have shown two very different algorithms, a simple shift versus a format-preserving encryption that involves multiple cycles, yet due to its strength is very difficult to hack. Among algorithmic features, the most important for data masking is the strength of the algorithms from the security standpoint. And today, we do a deep dive and explore two of the most common algorithms in detail. Oftentimes, in order to protect, we first need to understand how to break in, so we take a think hacker approach, explore a couple of ways to break the system, and show you how a well-chosen algorithm could protect your data in each scenario. In order to better understand how we secure the data, we first need to understand the properties of data while it is stored. The very first thing to understand is the fact that some data is unique and some is not. Data models a physical world. In a physical world, each person is unique, yet all of us have repeating attributes. Almost all of us are one of two genders, with outliers being such a small percentage of the total population that, statistically, you can assume approximately 50% of a given sample is one and 50% is the other. We all have names, and we all have age, and we live somewhere, and these properties are not unique. Many more people live in New York than in Aspen. There are many more Janes than Virginias. These statistical distributions are a powerful thing. The most famous example of a hack based on statistical distributions grew out of research from a graduate student named LaTanya Sweeney from Carnegie Mellon University. LaTanya linked the anonymized GIC database, which retained the birth date, sex, and zip code of each patient, with voter registration records to identify the medical record of the governor of Massachusetts, and later created the whole field of computer science and math, which deals with the so-called differential privacy. The essence of the case is reflected in the slide. LaTanya found that only 6 people in Cambridge shared the governor's birth date. Only 3 of them were men, and of them, only he lived in his zip code. Making further calculations, LaTanya defined that 87% of all Americans could be uniquely identified using only 3 bits of information: zip code, birth date, and gender. The threat is well recognized, and on top of many privacy laws in many industries, such as GLBA in the financial industry, FERPA in education, and many state laws, as well as HIPAA, the Department of Health and Human Services published a guide on its site on how to de-identify sensitive data. It's a safe harbor for making sure statistics is enforced in several of its elements, including zip code and dates. It does not mean that we should not take more protection, just these are the minimum requirements that people have to be aware of when masking data. Let's start now on the algorithms and explain the reasoning in several very simple examples. The first algorithm we will consider is shuffling. In shuffling, the data is shuffled within the column. No data is replaced per se, just the index in the column changes. In some sense, people define shuffling as a substitution with mapping to its own set of data. This algorithm is great for maintaining aggregates. An example application is when you need to maintain the end-of-year sales figure. Different algorithms are used for shuffling. The simplest one is shifting records along with the same number. Let's consider an example. Let's say we have a database of voters. For simplicity purposes, we will consider a database being a simple table with columns and rows. It has fields with unique values, license plate and phone number of the car, and repetitive values, such as name and gender. The example shows only the last few lines of the table. Let's look first at the initial database, with the number of records n equals 50 in production. After we mask the data and move it into the development environment, the masked database has the same number of rows, n equals 50, and looks like this. Please note that we employed a different shift for different columns, a +4 shift for the phone, +3 for license plates, and +2 for gender. Someone attempting to hack this algorithm would try to use data from the second masked table to restore the values in the first, the production table. One of the ways to do this is to enter a row with some unique traceable data, let's say a name, into the production table. Again, for simplicity, we assume in this example that the name does not shift. It should be noted that choosing a plausible, unique name is not difficult, for example, by changing one letter in the last name, since in real life there are no last names like the name Smith spelled with 2 T's or 2 H's. The initial production database with the new name is added, so the number of records is now n equals 51 and looks like this. After the masking cycle, we get the following database data set in production. And please see now the database with masked data of n equals 51. According to Table 4, the shuffle for unique data, the phone number and the car, is now easily defined. In the case of the gender, it would still be impossible. The probability of a correct correspondence between name and gender depends on how many women there are in the table, an original set for women. Since we are interested only in the correct sequence of the gender column, then the probability of being a woman is p equals 1 over the number of women. If the hacker knows how many women and men were originally in the table, he will insert a record with the gender that has fewer entries. Suppose in our example the basis is 20 women, 20 letters F in tables 1 and 2 in the column gender. Then the probability of a full recovery of the data set for the gender is p equals 1 over the number of women plus 1 equals 1 over 21. Security in data masking is all about the probability of de-identification. As we can see, simple shuffling is not a very secure algorithm. However, adding complexity to the shuffling algorithm will yield better results. Now, let's consider another algorithm that is also often used in data masking: substitution. Substitution is an algorithm in which another authentic-looking value can be substituted for the existing value. It is best suited for non-unique data. This is also an algorithm most often mentioned in the open source community. Here are the two blogs that we already mentioned previously: substitution for a unique social security number and substitution for non-unique names. Let's consider the latest example. In order to maintain the mapping table, you will have to get a distinct data set of names from production and create a mapping table that maps values 1 to 1. The author does acknowledge in the blog that security is not enforced to the fullest, but how strong will such a method be? Consider the following case. We want to determine the possibility of the correct diagnosis of a particular person in the database, presented in part in Table 1. We are assuming that the data in the database are collected throughout the United States and are represented proportionally, i.e., no female-dominated diseases or diseases specific to the state of Alaska. In this case, the data set is a representative sample of the patients. We believe that the database has 10,000 patients or rows. For masking data purposes, we replaced all the names in a one-to-one manner. For example, Brown is the original last name and is masked to Parton. Cook got masked to Nemeth, and Johnson got masked to Rickard. Now, after we masked the data based on mapping these substitution values, let's look at the resulting table. Suppose you want to discover the diagnosis of your colleague Johnson and neighbor Sook, as you want to know whether your colleague's disease is terminal, so you'll finally get that promotion, and whether your loud neighbor Sook will lose his voice forever and stop keeping you up all night. To do this, you implement a frequency analysis of last names. Using, for example, the site names.mongabay.com, you can see frequencies of the most common American last names. Since the sample of 10,000 is large enough, most frequently used last names will absolutely be guaranteed to occur in the appropriate proportions in the dataset. Since the names are masked in a proportion 1 to 1, new substituted names will have the same frequency of occurrence, i.e., the frequency of a substitution for the last name Johnson will coincide with the frequency of last name Johnson in the original set. And, based on the data frequency table of the above-mentioned site, it will be the second most frequent name. Obviously, this name is Rickard. The instance of this name in the database, with 10,000 data points, will be approximately 69. Your chance to correctly establish the diagnosis is then 1 in 69. Assume all diagnoses are unique. Let's say you know a small amount of statistical information about the dataset, that all the addresses are located in the United States. If you pick a state, for example, California, you can use some statistical information to further re-identify the dataset. According to the 2011 census, population in California is approximately 38 million people. The United States has, total, approximately 310 million people. The probability that a person in the database is from California is therefore 38 out of 311, or 0.122. Therefore, approximately 12% of the 69 instances of Rickard will be Californian, or about 8 people. The probability of guessing correctly is now 1 in 8. Knowing that Johnson, masked as Rickard, is a man, on the basis of approximately an equal ratio of men and women, we find that the probability of a correct diagnosis of the situation described is 1 in 4. If the last name is uncommon, for example, Sook, the chances of guessing are greatly reduced. In this case, it is impossible to ascertain the proper name of Sook in the new table. Using the table of the frequency of last names out of 100,000 from the site, determine the total percentage of names that occur less than 2 times in 10,000 values. This corresponds approximately to the uncommon last names. All names, like Sook, that are more rare than House, and House only occurs 15 times in the 100,000. Therefore, it will be assumed that all the names on the list below House in a 10,000 item list meet at least 2 times. The cumulative percentage of last names less common than House are approximately 37.5%, or 37,594.06 out of 100,000. Thus, any common single last name in a database of 10,000 values will occur in 62.5% of those values. Your chance is now 1 out of 6,250. if you know the information about the place of residence, state of California, then the names of 6,250 will be approximately 12% of Californians, i.e., 750 people. The probability of guessing is 1 out of 750. Knowing that Suk is a man, we find that the probability of a correct diagnosis of the situation is approximately 1 out of 375. Probabilities increase when we don't do one-to-one substitution and increase the disturbance in statistics. There is a lot of work being done in this area in different research labs at major universities, at Microsoft, and other companies. We translated this research into the product so that you don't have to. As we can see, the simple algorithm mentioned in the blog provides little security, if at all, and is not the best way to spend time and money, and it is worth mentioning that there exists a much stronger algorithm that we will be glad to explain upon request. Thank you and have a good day.